Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 1, Lesson 9 on parallel lines. Now, you've all heard of parallel lines, you've been probably talking about them since grade school. So let's get right into it. Parallel lines are critical. One of the most important ideas in plane geometry is that of two lines that don't intersect. Those are known as parallel lines. So right away, I want to make sure that we understand something very straightforward. Let's take a look at exercise number 1. Two lines M and N are shown below. Even though in the diagram they do not seem to intersect, use a straight edge to extend the lines and find their intersection point. All right, so why don't you go ahead and take your ruler and extend these lines, because remember, lines, no matter how we draw them, do extend forever in two directions. So these two don't, in the picture at this point, touch, but use a straight edge to find where their intersection point is. All right, well, for some reason I didn't give myself a straight edge, but you can kind of see it, right? If you extend this line, and if you extend this line, eventually they're going to intersect, right? There's going to be an intersection point. And you can really tell that, right? Because the distance between the two lines, right? If we kind of look at how far the two lines are apart, it's very clearly obvious that that distance is getting smaller. And so eventually, since the two lines extend forever in a given direction, they will intersect at some point. So let's make sure that we've got the definition of parallel lines and parallel line segments down. Two lines that have no points in common, i.e. they don't intersect, are known as parallel. We say that AB, line AB, is parallel to line CD. Two segments are parallel if they are parts of two parallel lines. All right, so real simple, right? Parallel lines do not share points with one another, i.e. they don't intersect, and they come up all the time. Let's take a look at exercise number 2. Often we can informally judge whether two lines or two line segments are parallel by simply looking at whether the distance between the two lines is changing or not. For each set of lines below, circle those that appear parallel. Okay, so I'd like you to go ahead and do that, right? I've got 3 sets of lines. If you think that they're parallel, circle them, and if you don't, don't. All right, so again, the idea is if I kind of looked at this distance, does it seem like it's getting smaller? And the answer is no, it seems like it's remaining the same. So those two lines appear like they're parallel. Now again, I know I've got some geometry teachers right now that are cringing and going, you should never judge anything based on a picture. Yeah, maybe. I would maybe dispute that, but we can't argue right now because you're not in the room with me. Anyway, geometry is a lot about observation, right? And then proving your observations. So right now, I'm not proving anything. I'm not proving these lines are parallel and these lines aren't, you know. I'm just saying, look, this is the way it looks like to me. And here, the distance between line A and line B appears to be getting shorter, right? So those are not parallel. Now, E and F. You might think, well, E is much shorter than F. Nope. Lines are lines. They are infinitely long, right? That also appears to be a distance that's not changing, so I think that those are also parallel, okay? Now again, right, there's no proof here. We're just trying to get our fingers wet, our feet wet with parallel lines. All right, exercise number 3. There are many types of polygons that have side pairs that are parallel. For each of the following, state the side pairs that are parallel. All right, so again, this is all based on pure observation, or if you know the definitions of these figures, it's not based on observation, but assuming that you don't, try to figure out what you think are parallel and make formal parallel statements. Pause the video now and try letter A. All right, so let's dispense of something right away. Something like side AB and side BC are certainly not parallel because they intersect at point B. So any two adjacent sides obviously can't be parallel. The question is, sides that aren't adjacent? Are they parallel? Well, side AD, right, this, and side BC, these aren't parallel because eventually they'd intersect maybe somewhere up there, all right? But side AB, let me maybe go different color, side AB and side CD, well, they are certainly parallel, okay? And in fact, we can mark them by doing little arrows like that. Oh, I thought I'd gotten back to blue, but I didn't. All right. Now, I'm going to say that AB is parallel to CD. Be careful. The parallel symbol looks a lot like the equality symbol, and that is not a coincidence, by the way. All right. In fact, the equality symbol is actually based on the parallelism symbol, but that's historical and we don't need to worry about it. All right. Don't tell me that AB is equal to CD. All right. That would in some way imply that the two segments were congruent or the same length. Now, if we look at this parallelogram, parallelograms are awesome because opposite sides are always parallel. In other words, HG is parallel to EF and HE is parallel to GF. All right, I can write that like HG is parallel to EF and EH is parallel to FG. Okay, what I'd like you to do is pause the video and see if you can write down the parallel line pairs for regular hexagon KLMNOP. All right, well, it's probably pretty obvious. PK is parallel to NM. All right, KL is going to be parallel to ON. And finally, OP will be parallel to ML. So parallel lines and parallel line segments, even more often, come up a lot in geometric shapes, okay? Probably the most common geometric shapes that you think about, except for a triangle where there can be no parallel side lengths because they all touch each other, right? Parallel line segments come up a lot, all right? So let's play around a little bit more. Now let's talk about angles that are formed by parallel lines. When any two lines are intersected by a third line, and those could be parallel or not, all right, that third line is known as a transversal. 8 angles are formed. All right, 4 angles are formed when that line crosses one of the lines, and then 4 angles are formed when the line crosses the other line. Anyway, there are many different angle pairs that arise from these 8 angles. That's right, we're back to our angle pairs. Unfortunately, they all have names, okay, these angle pairs. But thankfully, again, all the names have some kind of descriptive terminology to them that will help you understand where they're located. Let's take a look at exercise number 4. Given parallel lines R and S crossed by transversal line T with the 8 angles marked, state each of the following. Letter A. What appears to be true about all acute angles in this diagram? Verify using tracing paper. So, right, let's be clear, there's 4 acute angles, right? There's angle 2, there we are, angle 4, angle 7, and angle 5, right? And we can just base that just on judgment. Now, what appears to be true about those 4 acute angles? Pause the video now and maybe test whatever you think with tracing paper. Well, it kind of looks like they're all congruent. All right? They are all congruent, right? They're all the same size. Now here, right, if I put this angle just like that, right, my tracing angle, there's angle 2, all right? I can very quickly tell that it's the same size as angle 7. Right? It's very easy to just sort of shift it down like that. It's a little bit harder to tell if it's congruent to the other 2 angles, but if I just rotate it and I bring it down here, I can then see that it is congruent to angle 5, and then it's simple enough to slide it just up here, and I can tell that it's congruent to angle 4, right? So all the acute angles are congruent to each other. And not surprisingly, all the obtuse angles are also congruent to each other. They're not congruent to the acute angles, that would be impossible. They are all congruent. Okay, and again, we can do exactly what we did before. Let me go around the bend, right? So here's my first angle. Let me get rid of my blue angle. There's angle 1. I can very quickly translate that down here and see that it's congruent to angle 6. I can rotate the angle, which doesn't change it at all. And I can see that it is congruent to angle 8, and then I can shift it up, translate it up here, and see that it's congruent to angle 3. So it's kind of cool, right? If you just want to think about angles that have the same degree measurement formed by parallel lines, then all the acute angles are congruent and all the obtuse angles are congruent. Now let's get into all the nitty-gritty terminology. Now again, we're just introducing this terminology right now. We'll eventually work a lot more with parallel lines where we get use with all of these terms. But let's see what they all are. Letter C. List each corresponding angle pair. Parentheses, same relative place where the lines cross. All right, let me just get rid of my blue angle and let's talk about corresponding angles. Okay, so if I look at just this up here, this area up here, all right, and I kind of ignore this, and I look at angle 1. Angle 1 is in the upper left-hand corner up here. What angle is in the upper left-hand corner of this sort of X shape down here? Well, that's angle 6, right? Angle 1 and angle 6 are in the same place. They're in the same corresponding location. So angle 1 corresponds to angle 6. See if you can write down the other 3 corresponding angle pairs. All right, well, angle 2, right, upper right-hand corner, corresponds to angle 7, also upper right-hand corner. So angle 2 corresponds to angle 7. All right, and then let's nail out the last 2, right? Angle 3 then, which is below angle 2, will correspond to angle 8, which is below angle 7. So angle 3 corresponds to angle 8, and angle 4 corresponds to angle 5. All right. Corresponding angles are absolutely critical when it comes to parallel lines. Now let's talk about ones that have kind of more confusing names. Letter D. List each alternate interior angle pair, opposite sides of transversal and inside of the parallel lines. So let's talk about it, right? We've got interior angles and exterior angles. The interior angles are the 4 angles that are inside of the 2 parallel lines. The exterior angles are the 4 angles outside of the 2 parallel lines. If I'm talking about alternate interior angles, anything that alternates is on either side of the transversal, okay? So one alternate interior angle pair would be angle 7 and angle 4. Right? Angle 4 and angle 7 are alternate interior angle pairs, right? Because they're on the inside of the parallel lines and they're on alternate sides of the transversal. But there's another pair that's an alternate interior pair. That was kind of cool. Didn't mean for that to happen. But that would be angle 6 and angle 3. Those are also inside but on opposite sides of the transversal. So angle 3 and angle 6. Alternate interior angle pairs, absolutely critical. Let's take a look at letter E. List each same side interior angle pair. same side of the transversal, and inside the parallel lines. See if you can list these two pairs. Well, again, the interior angles are 3, 4, 6, and 7. Okay. Same side interior angle pair means same side of the transversal. So that would be angle 3 and angle 7. That's one pair. Angle 4 and angle 6. That would be the other pair. Those are same side interior angles. Not bad. Now let's talk about the exteriors, right? We've got 4 exterior angles. Angle 1, angle 2, angle 5, and angle 8 are exterior. Let's list the alternate exterior angle pairs and the same side exterior angle pairs. Not pairs, that's different. All right, let's pause the video now and let's answer G and F. All right, so on this one, right, list each alternate exterior angle pair. Let's see. 1 is exterior and alternate to 8, so angle 1 and angle 8. And 5 and 2 are exterior, so angle 5 and angle 2. All right, now same side exterior angle pairs. Okay, that'll be angle 2 and angle 8, and angle 1 and angle 5. All right. Now let's do the last problem here. Letter H. If the measure of angle 1 equals 125 degrees, then determine, based on A and B, the measures of all other 7 angles, state them below, and label them on the diagram. All right, well, I say we just kind of throw these things on the diagram, right? What we talked about in A and B was the fact that all the acute angles are congruent to each other, and all of the obtuse angles are congruent to each other. So if the measure of angle 1 is 125 degrees, now watch, right? 3 has to be equal to 125 degrees as well, because those are vertical angle pairs, right? We've talked about the fact that vertical angles are congruent. Now angle 2, on the other hand, has to be supplementary to 125 degrees, and that's going to be 55 degrees. Angle 4 also has to be 55 degrees because it's a vertical angle pair. So even if we didn't have parallel lines, even if we didn't have this second line at all, if 1 was 125 degrees, then 2 would have to be 55, 3 would have to be 125, and 4 would have to be 55. No getting around that. All right. Now here's the key. Corresponding angles will always be the same. So if 1 is 125 degrees, so is 6. If 2 is 55 degrees, so is 7. So this is 125 degrees, number 7 is 55 degrees, number 8 is 125 degrees, and number 5 is again 55 degrees. Simple enough. All right, so let's keep going. Let's talk about one final thing having to do with parallel lines, at least for the moment. A surprisingly important assumption. Let's talk about the parallel line postulate. Given line M and a point P not on line M, there exists only one line that can be drawn through P that is parallel to line M. So when geometry was originally kind of formalized, it was a long time ago, about 2,500 years ago, that's 2,500 years ago, by a guy named Euclid. Okay? This is why a lot of what we're doing is what's known as Euclidean geometry. And one of the things that Euclid decided on was that if you have a line and you have a point not on the line, there's one and only one line that can be drawn through it that is parallel. Why don't you go ahead and see if you can just sort of eyeball that line. You can use a ruler, or you can kind of just do it by hand. Try to draw a line that passes through P that is parallel to line M. All right, well, this is simple enough for me. I'm not going to use the ruler because line M is a horizontal line, so there it is, right? That is the one and only line that will pass through P and also be parallel to M. Now, this is a postulate. It's something that's assumed to be true, but it feels right, right? Because, right, let's say we took this line, still made it pass through P, right? If in any way we change that line, just a little bit, right, then what's going to happen is eventually it's going to intersect line M either over here, or it might intersect the line over on this side, right? So it just feels right, this idea that, right, there is only one line that can pass through that point that will then never intersect this line, because if I change the slope of that line even a little bit, it will eventually intersect line M, the parallel line postulate. All right, let's summarize a little bit. We did a lot today with parallel lines, right? We talked about simply what a parallel line was, the fact that parallel lines or parallel line segments arise in a lot of common shapes that we work with, like parallelograms. Who would know, right? Then we looked at all of this angle terminology having to do with parallel lines, and I'm not going to even try to review that right now. All right, and then we finally took a look at the parallel line postulate, the idea that if I have a line and a point not on the line, there's only one line that can go through that point that will be parallel to the line that's given. All right, all important stuff. We'll see it all come up again and again in geometry. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.